Alright, so today we're going to go over sensor types and how to choose the correct sensor for a control system. One of the questions that came up was, how does a data sheet tell you, other than input or output signal type, how a sensor should be matched to a system on what you're actually measuring? Like, you could have a proximeter that measures anywhere from 0 to 12 inches, but because you're measuring something that goes from 0 to 12 does not mean that that sensor is viable. As a matter of fact, it's entirely the opposite. It may not work for any part of the system other than the minimum and the maximum and some range in between. So when you pick it, you have a signal output type, signal output range, and you also have a signal input type. You have a signal output resolution, and you also have a voltage range, and yeah, we'll start with those. So let's say you need to measure 12 inches. From 0 to 12 inches, we'll call it a level sensor, an ultrasonic. So an ultrasonic level sensor, we want to measure 0 to 12 inches. And we have to do this in a specific accuracy, or I should say, yes, a specific accuracy. There is a difference between accuracy and precision. Precision is the ability to keyhole the same shot. Accuracy is the ability to actually hit what you're aiming at. So 0 to 12 inches, and we'll call it 1 inch increments. So now we need all of these for an ultrasonic sensor in order to get that read at no less than a 1 inch increment. So if we go to measure 2, 4, 6, 8, 10, 12, that's not going to work, because at some point one of our highs, lows, or low alarms may go off based on this reading 1.5 when it's trying to read a 2. It's going to round down to the next significant point that it can actually measure. So voltage range, we would say normally in most cases, if it's a transistor or a gate saturation device, you would usually have a 3 to 32. Sometimes it's a 0 to 5, 0 to 10. You could have plus or minus 10. You could have 4 to 20 milliamps. So I guess voltage range, there we go. There, you could have current or voltage range. And these would all be VDC, 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 and so on and so forth, and you would have multiple ones of these. So signal output type, we'll say we're going to feed it back to a module, and that module is what is going to populate the plant computer system. Well, we have to know what that module receives. Do we want it in 4 to 20? Do we want it in 0 to 10? What does the module receive from its minimum to maximum range of signal input type at the processor? So for signal input type, we'll say it's feeding back to a 0 to 10 volts DC system. And that's what's actually going to be reading what's coming off of the sensor. So when it comes back as a 0 to 10 volt system, what we want to be able to do is, first of all, what's going to be the supply power, and also what is going to be the receive back. So when we pick this out, let's get some of this stuff out of the way. When we pick this out, we want to measure from 0 to 12 inches. So when we pick this ultrasonic level sensor, and we know that the module on the other end is a 0 to 12 volt, or sorry, 0 to 10 volt DC discrete input. Okay, so we're going to have high highs, low lows, highs and lows, alarms. So let's put some alarms in here too. Let's start to build what our sensor actually needs to be. We're going to move this over a little bit. So that's our lowest, and that's our highest alarm. Now, what we're going to do is we're going to have a range, or a limit of range. And this is how this is going to work. So, because we have a module for 1, we need to have anywhere from 0 volts to 10 volts to measure it. That gives us our 0% and our 100%. So we would essentially set our levels highs, highs, lows, and lows, right? No, that is not correct because of the fact that currently we're in an industry 4.0 developing into an industry 5.0. 5.0 is going to be AI, which essentially is just an algorithm that knows the same thing humans do, but thinks on their feet a hell of a lot faster. So there's two things that make the 0 and the 100% marks wrong. That would be what the site wants to see, minimum, 0 to 12 inches. But when you go into a high alarm, you will go over here. High alarm is somewhere in the actual max range. Low is somewhere in the minimum. And low, in this case, probably wouldn't apply unless the 0 inches could be water to a cooling system and that pump may cavitate below a certain point. So you may have 2 feet of water underneath, but at that 24-inch mark, you have a low alarm where it's reading 0 inches, which means it's no longer usable to the pump below 24 inches. So that 0 is pretty much your out of water for making sure that you have net positive suction head. So what we would do is not call that or that what we need. So 0% is essentially minimum or minimal value of feasibility. And the 100% could be maximum value of feasibility. 100% in some cases if you weren't feeding a pump exactly. This is kind of a universal term and it is written how it needs to be written depending on the system you're designing. When we say maximum value of feasibility, that could also be if there's a valve at a really low place that's taking on a lot of pressure from just the water column effect, which is rho GH, and we would figure out that the maximum value of feasibility, if you put a high alarm on this, what you're saying is that you may get leak by on a globe valve or a gate valve, possibly a butterfly could open by accident if you have too much head on the suction side of a valve. So this would be where the plant wants it to stop. This is where the plant wants the lowest range to possibly be. Now the reason why we don't consider these 0 and 100% of the range of the input module is because of a thing called a PID, proportional integral derivative. PIDs do not operate on 0. Calculus differentials do not operate on 0, or there wouldn't be a differential, so it essentially cannot use 0. That is why when you look at a 0 to 20 milliamp module, below 4 milliamps or somewhere in like the 3.0 range on some controllers, you will find that 0 to 3 is actually considered not usable. So what they do is they make all the sensors 4 to 20 milliamps, but the modules can do 0 to 3 or 0 to 20. So the module is much more capable of reading an input and it can compensate. You cannot compensate on a sensor. It puts out what it puts out. That's what the chip or the small SMD circuit driver in it is actually programmed or set up to do statically. So you would set, we're doing a 0 to 10, so we'll call this 1 volt to 9 volts. And another reason you would sit there and make it inside the range instead of making it completely and totally across the full range is you have manufacturing and QC tolerances that don't always mean 0.000000 or 10,000,000. Nothing is ever precise. There's no such thing. Otherwise, one manufacturer would monopolize the entire planet. So what we do is we set it inside of the range for tolerances, allowances, potential fluctuations. We do not want to have something down here going like this on a graph, and the only thing we can see is this. We do not want something to show up in what they call harmonic distortion, clipping, total distortion, whatever you want to call it. That's not okay, because our alarm line might run all the way across here. What you're doing is you're about to be above the alarm, so the low alarm or the high alarm, depending on what the sensor outputs, if it's 10 to 0 or 0 to 10, you would never see it. So to be sure, you put it inside of the range of the sensor. Now remember, we sat there and we said we need to be able to measure every inch. That is our maximum resolution needed. So how do we pick a sensor for resolution? You're not going to get on a data sheet and have something say, oh, it's 0 to 10, and it's going to measure in volts, about 1 volt per increment. It's not going to happen. What you're going to see is something like, say, actually, what you're going to see is this sensor is 13-bit resolution. What does that mean, 13-bit resolution? Well, I'll tell you what that means. 2n minus 1 equals r to the n. Now what does that mean? Okay, n equals number of bits. That's what that means. So in this case, we have 2 to the 13th minus 1 equals rn. 13-bit, I believe, is 8191, if I remember correctly. So 2 to the power of 13 is 8192 minus 1 equals Rn, which gives you 8191 points of measurement. What does that mean? So, for our 0 to 12 with 8191, that means with a 13-bit sensor, or what we can more commonly call it, can't write today, or more commonly known as a transducer, depending on where you work, we get 8191 points that we can actually look at. So when we look at this right here, our 0 to 10 range is going to be 819.1 little measurements before it hits 1 volt. So between here and here, we can fluctuate 819.1. The way I got that was, it's over 10 volts, you would divide this number by the number of volts you're trying to read. We need to see 12 in this range. So over here, we have 819.1. We have 819.1 above. And over here, we have 819 below. So now we have our buffer. If this transducer comes back and it's a little bit out of range, that's okay, as long as it passes calibrations, the NIST ones, not hooking it up to a multimeter. And we'll get into why multimeters shouldn't be trusted, especially the Fluke 289 for 700 bucks. It doesn't actually do automation that well. Okay, so we have 819.1 over there and over there. So now what we need to do is figure out how much range we have in between. We have 6552.8. So from here to here, 6552.8. That is how many, if I were to put tick marks in here like 16ths or 32nds of an inch on a ruler, you're essentially doing the same thing. If you have a 16th inch increment ruler, you can measure in 16ths. That's your resolution. So whatever 16 would be, you know, it'd be 2, 4, and then 16. You have a 3-bit ruler if it's measuring in 1 and the 16th of an inch. So between these 2 points, we need to be able to measure in inches for sure. Well, I'm pretty sure there's not 6,552.8 inches inside this range here. So one 13-bit resolution is good. But how many bits can we measure per inch? Well, that's simple. We would divide this by 12. And that gives us 546.06 repeating. So 546.06 repeating all the way down. In this case, even in a floating 32-bit integer, you're probably not using anything past the thousandths position because of the small measurement that it is. And unless you're measuring the lake, you probably don't need it. So we're going to call it 7. And that is per inch. So if we do this, what exactly can we measure? So we will divide 1 inch by 546.07. Units matter. So what we can actually measure this entire time is we can measure about 2,000 per number on here. So that's how close we can get. This 13-bit sensor will measure 2,000ths of an inch. Now, when we start getting these little tiny points out here, this 0 to 10 volts, this is low amperage. This is like barely excited by the actual system, because the system has comparators in there, transistors, rectifiers, current limiting shunts, and they micro weld all of these things, that little circuit board in there, or they reflow, or they solder paste them in. When those go in, this is putting out a very low amperage, maybe 2 milliamps. Your multimeter is not going to pick that up. If it does, you got lucky. So when you go to look this up, the best thing you can do is use an oscilloscope and see what the DC meter on there is. A DC coupling setting actually shows on the scope. Make sure your scaling's right, make sure you're looking at the same time graph, everything, you'll be fine. Alright, so let's go over some of the things that could cause issues when reading a sensor that's in fail, or reading high, reading low, it's sporadic, it's spurious alarms, things like that. So, like I said, with the resolution thing, depending on what the PLC can read is what's going to dictate whether or not you get that kind of a sensor. So while the sensor is putting this out and you're getting alarms and problems are happening, you need to remember that resolution also applies to frequency and the range of view. So when you're reading this stuff on like an HMI, or you're looking at graphs on Pi tools, or you're looking at something on a multimeter, maybe a Fluke 190 for a portable oscilloscope, 2 and 4 channel, things like that, you should be cognizant of the idea that this might be talking faster than the tool you're using. That is why at the beginning I said use an oscilloscope. It's because an oscilloscope is made to design electronics. Everything else is made to test them. Granted, the problem isn't between the driver's seat and the steering wheel, when 90% of the time it is. Like I said, this is only going to put out like 1 or 2 milliamps of a signal, regardless of what the excitation voltage or power supply voltage is, because the PLC is not a giant heatsink. So when you read this stuff, make sure you're reading it at the sensor. Work your way from the signal source to the signal receiver, checking connections. Make sure you don't have inductive feedback on your lines. Make sure they're not in a bad cable tray to ground. Know the difference between earth and ground. Things like that play a huge role in diagnosing problems with these things. You have to know how to read the drawings. You have to know what the P&ID charts say. You have to know what kind of equipment you actually have using to actually figure out what's going on with this. You're not going to see this. This is all in the automation control side of the house. This is not going to be on any tools. I have a tool that I have used recently to actually get these values though, and these values are only good if you set your significant digits on the PLC that's reading them. And I will show you what that tool is. So, this is the system that I use when I want to read what a transducer is doing, but I want to read it the way the control system is doing it. I wired this up so I could do 3 things. One is produce 3-phase outputs that could test a motor up to 40 amps. And then it has DC over here, and what these are for is these are for modulating, in my case anyway. I use them to modulate signals going into a VFD. This will also read high-speed inputs. It'll also read 0 to 10, 4 to 20, all the way down to 0. And this checks the capacity range of individual transducers on those 2 setups. This will not do a pulse width modulator reading, but it will pick up frequency. So that's the one bonus to it. And this will also put out high-speed PWM up to, I believe it is 10 kilohertz I have it set up for. Now that's a whole different topic, but based on your inductors and the size of your capacitors will dictate how fast this will move. Just like in a car stereo, you have filtering capacitors and you have filtering inductors. Well, eventually it can't discharge faster than the pulse, so you just get a nice DC signal. So that's where this comes in, provides power to everything. Where these things come in is they only work up to a certain range. And that's all I got for this one. Hope it helps with some of the ideas of how sensors work. And this is an oscilloscope. Not an oscilloscope. This is an oscilloscope. This is not an oscilloscope. Not a scope. So if you want any more videos like these, please subscribe, like, or comment on this stuff, and I will see what else I can get out there. Thanks, guys.